Homework 1, problem 10. We are here to test Stokes' theorem for the following vector function over the following surface. Stokes' theorem says specifically that the surface integral over some surface S of the curl of a vector function is going to be equal to the closed line integral over the boundary of that surface of that vector function. So in order to test this, we have to evaluate both sides. And so I'm going to do the left-hand side in red and the right-hand side in green. For the left-hand side, first we will use the right-hand rule, and the arrows which are already drawn on our edge give us that the normal, our n hat for the surface, is in the k hat direction. Now we need to take the the curl of our vector function. By definition, the curl of a vector function, v, is partial v, let's see how to do this, partial vy over partial z, no, sorry, sign, partial vz over partial y minus partial vy over partial z I hat plus partial vx over partial x minus partial z, partial vz over partial x j hat plus partial vy over partial x minus partial vx over partial y k hat. Now first, if I'm taking n hat vector onto the curl, I only need to evaluate the y component, and so I can write down n hat dot curl of my explicit f is going to be, this is going to be the partial of f with respect, the partial of fz with respect to y, which is 0, minus the partial of fy with respect to z, which is going to be 2y. Okay? So now we need to figure out what the area is for our system. Our area integral d to x is going to be an integral from 0 to 2 of dz and an integral of 0 to 2 minus z dy. And so that's just what it's going to be. So on the left-hand side, integral over s d to x of n hat dot del cross f is going to be the integral from 0 to 2 dz, the integral from 0 to 2 minus z dy of minus 2y. Continuing on, this integral is fairly easy to evaluate. This is going to be the integral from 0 to 2 dz, and then it is going to be minus y squared evaluated at 0 and 2 minus z, which is going to be the integral from 0 to 2 dz of minus 2 minus z quantity squared, which is the integral from 0 to 2 dz of minus z squared plus 4z minus 4, which is then minus 1/3 z cubed plus 2z squared minus 4z evaluated at 0 and 2, which is minus 8/3 plus 8 minus 8. And so from the surface integral, we evaluate minus 8/3. To evaluate the line integral around the edge of dl dot f for our system, we're going to break this into 3 parts. I've labeled them 1, 2, and 3 here. For part 1, we are going to find that dl, the direction of dl at least, is in the minus k hat direction. And along this line, we have z goes from 2 to 0 along the z-axis, which says that x equals 0 and y equals 0 along that line. When I have k hat dot f, I can see, here, where's my f? There we go. I can see that f is 3zx. At x equals 0, this is going to be 0. So I'm going to have no contribution from the first part. For the second part, I can see that the direction of dl goes from the origin out to 2 along the y-axis. The direction is going to be positive j hat, and I'm going to have that y equals 0 and z equals 0 along that path. So k hat dot f vector is going to k hat j hat dot f vector is going to give 2yz, but at z equals 0, this is going to give 0. So I have no contribution from either leg 1 or leg 2. So the final thing is to evaluate the contribution for leg 3. For leg 3, we have to parameterize the path, and so I have to worry about 2 things. I have to worry about what dl is, and specifically I have to worry about what this is, the integral of dl vector along this path 3. I'm going to parameterize it in terms of arc length, and so I'm going to say this goes from 0 to 2√2 dt, and then the direction of dl, the unit vector, is in the minus y direction, positive z direction, equal amounts, and so that's going to give me the unit vector. When the actual path that I pass through, my r vector as a function of t, the x component is going to be 0, so this will be 0 I hat. The y component is going to start at 2, so at t equals 0, it starts at 2, and then at t equals 2√2, it should be 0. And so when t is 2√2, I get 2 minus 2, and this gives me 0. So that's the y component. And the z component is similar, but backwards. At time t equals 0, I'm going to have 0, and at time t equals 2√2, I want the value 2. So this is my k hat component. And so this is the parameterization of the path in terms of arc length t. Go ahead, going along and filling out the integral. We have the integral from 0 to 2√2 dt. And now we're going to get a little bit fancy. I have j hat dot f. And so j hat dot f, or no, let's say that I'm going to get this k hat dot f. So f k hat is 3zx, x is 0 along the whole line, so I'm going to ignore the j hat. I'm going to ignore the k hat dot f part of this. I'm only going to evaluate the j hat dot f. So pulling out the minus 1 over √2, then I have now the j hat component of f. And so f is still there. This is going to be 2. The y is 2 minus 2 2√2t. And the z is 2 over 2 root 2 t. And so I need to evaluate this integral. We can do a little bit of simplification. The 2 can come out, this 2 can come out, and this 2 root 2 can come out. They multiply everything. 2 times 2 is 4, so I'm going to get minus 4 on top, and 2 root 2 times root 2 is 4, so I'm going to get 4 on bottom, which is just 1. Integral 0 to 2 root 2 dt. And now the t can go through, so this will be 2t minus 2 over 2 root 2 t squared. Evaluating this integral is going to give me minus, I still have the minus sign, and then the 2t is simply going to be t squared, and then minus the t squared is going to give me 1/3 2 over 2 root 2 t cubed. And this is evaluated at 0 and 2 root 2. I see that the 2 root 2, when I plug in one of those t's, will cancel down here at the bottom. And so this is going to give me 2 root 2 squared, which is 8. So minus 8 minus 1/3. 2 times 8, so 16. Getting the lowest common denominator, this is going to be minus 24 thirds minus 16 thirds, which is minus 8 thirds. And so this also gives me minus 8 thirds. So I have minus 8 thirds for both the surface integral and the line integral. Therefore, Stokes' theorem works.